So one thing you'd want to know to answer question 121, or to think about it, is you would want to know what sigma and pi bonds are. And to understand what those things are, we'll want to go back and talk a little bit about atomic orbitals. And for those, we'll even want to go back and just touch on very briefly how the atomic world is different from the macroscopic world. The macroscopic world that we live in every day appears to be fluid. It seems like you could move in any way. It's sort of like a television where it seems like you could have any color at all: mauve, taupe, orange, blue, any possible color you could think of. You think that it's fluid spectrum of infinite colors can appear on a TV. But if you zoom into the screen on a TV, you would see that there's a bunch of little lights, and each light can only be either red, green, or blue. And so whereas macroscopically the TV looks very fluid, on a microscopic scale, there are only a certain number of possibilities that the colors could have. And similarly, on the macroscopic world, we can move in any which way we want. But on the microscopic world, electrons flying around the nucleus of an atom can only move in a certain number of ways. Because they can only move in a certain number of ways, they're called quantized. And that's where you get the term quantum physics. It's how things move on a scale where only certain things are allowed and nothing in between. So if the macroscopic world is like a ramp where you could stand at any point, the microscopic world is like a staircase where you can only exist at certain places, at certain levels or heights. So if an electron is moving around, you have this tiny, tiny atom. If an electron is flying around that atom, and it's flying at over 4.5 million miles per hour, it flies, it blurs, sort of like if you're trying to take a picture and somebody's moving, they blur. And it can only blur in a certain number of ways. The ways that it can blur is quantized. At the lowest energy, it would blur into a sphere. And so, because it's a sphere, it's called an S, and the blurring area is called an orbital. So that's an S orbital. If it gets a little bit more energy, it can blur in the shape of a peanut. Now, that is also an orbital because it's an area where an electron is blurring, but because it looks like a peanut, it's called a p orbital. And so these are the orbitals that atoms tend to have, the atoms that we deal with in organic chemistry. And bonds tend to form when these orbitals start overlapping or bleeding into each other. Imagine you had electrons on different atoms both flying in s orbitals, and they get really close, so their orbitals start to overlap. So they would almost be as if they flew in a sort of oval like that. That overlap is what the bond is. And so this is going to be a bond. And if you get this overlap without any interruption, notice the overlap isn't interrupted in any place. Overlap without any interruption is called a sigma bond. The Greek letter sigma, which looks something like that. So that is overlap between orbitals without any interruption. This type of bond can actually be formed between almost any different orbitals, but because it's usually formed between two s orbitals, it was given the name sigma, which is the Greek letter for s. This is the first bond formed between two atoms. The first bond formed between two atoms is always a sigma bond. Okay, let's compare that with if you had two p orbitals instead of s orbitals. Imagine you had a p orbital here and another p orbital here. And you can see that if they get close to each other, they do line up. But there's an area in the center where the overlap is interrupted, the red area. So this type of bond is actually weaker than a sigma bond. Because this bond is usually formed from two p orbitals, it's named after the Greek word for p, which is pi. So this is a pi. That's the symbol for pi bond. And the technical definition is this is where you get overlap between orbitals, but it's with one interruption. And that's that red area there. So this is actually going to be a weaker bond. Pi bonds are weaker bonds than sigma bonds because there isn't full overlap. There's this area here where the orbitals are not overlapping, and that makes the bond weaker. This is every bond. In organic chemistry, this is going to be every bond formed after the first bond. Between every bond formed between two atoms. After the first bond. Okay, so like if you had a double bond or a triple bond, the first bond is a sigma bond and the other two would be a pi bond. Okay, notice to make this pi bond, the p orbitals have to be parallel. If one of the p orbitals is pointing up and the other one is pointing out, they don't overlap at all. And so, in order for the pi bond to exist, the p orbitals have to be parallel. And that's significant because if you have that type of a bond, you can't rotate it. If you rotated it, this one would stay the same, this other one would want to move. And if that rotates, notice it doesn't overlap anymore. So you've destroyed the bond. And that is energetically unfavorable to break that connection. So these pi bonds tend not to rotate. They can't rotate. So if we go back to this question, it said sigma bonds experience free rotation. They can rotate. See it moving right here. And you know this is a sigma bond because there's only one bond there, and sigma bonds are the first bond formed between two atoms. So this bond can rotate perfectly fine. But they say pi bonds do not experience free rotation, and they want you to explain. And for the explanation, you would want to draw out these two like prototypes for the sigma bonds and pi bonds, and you would want to talk about how, in order to have a pi bond, two p orbitals have to overlap, and for that they have to be parallel, because if you rotate one of them, if you rotate one of them, the p orbitals can't overlap anymore. And so it would break the bond. And that would be the explanation for that one.